Today we will discuss basic computer organization. This is the first part of our lecture 6. Now, what is our objective today? Our objective is to have a look at the instruction codes, stored program organization, indirect address, as well as direct addressing schemes, computer registers, and common bus system. Now, let us try to understand what is instruction code. Well, basically, instruction code is a binary code which actually specifies a sequence of micro operations for the computer which is under consideration. Now, the instruction codes, which are binary in nature, as well as the operand or the data, are usually stored in the same memory module. Now, the computer, as we all have studied earlier, the computer usually has three basic modules. One is the central processing units, another one is the input-output section, and another one is memory. By default, the computer communicates with the memory, and the instructions that the computer understands is basically loaded into the memory, and the instructions that are going to work on the operands are also stored in the same memory module. The computer reads each instructions one by one from the memory until and unless it encounters a jump instruction and places that into the control register where it is actually decoded. Then the instruction is decoded and proceeds to execute it by issuing sequence of micro operations. Means apart from so many instructions that the particular computer understands, any one of the instruction is decoded in the decoder. That thing is passed on to the timing and control unit, where the timing and control unit issues different sets of control signals in sequence to complete a particular task which has been mentioned in the instruction code. Those sequence of signals are basically called micro operations. Every computer, we are considering a hypothetical computer here, so it will have its own unique instruction set. So every computer has its own unique instruction set. The ability to store and execute instructions, that is the stored program concept, is the most important property of a general purpose computer. Okay, now an instruction code is a group of bits that instruct the computer to perform a specific operation. The most basic part of an instruction code is the operation part of it. The operation code of an instruction is a group of bits that define such operations like we can instruct the computer to go for addition operation, to go for subtract operation, to go for multiplication, shift, complement. So these are the operations that our computer has to perform, and the computer will perform these operations only when it encounters that particular instruction code. So the instruction codes are defined in the computer, and when that particular instruction is decoded, the computer will start the operation as per the instruction provided. The number of bits required for operation code of an instruction depends on the total number of operations that are available for the computer. So suppose a computer is having 16 operation codes, so we may require 4 bits, that is 2 to the power 4 is 16. So 4 bits can define all the operations of that particular computer. Now the operation cost must consist of at least n bits for a given 2 to the power n or less distinct operations. So let us try and understand a computer which is having 64 distinct operations, one of them being an add operation. Now we are just taking a hypothetical computer and we're just taking a typical example here. So let the instruction code be 110010. So the operation code consists of 6 bits. Here the 6 bits are 110010, which has been assigned to the add operation. I'm not saying that this will be the same for all computers. We have taken an hypothetical computer. In the computer that we are considering here, the instruction code for add is 110010. Now the operation code is decoded in the instruction decoder. Then, as we can see, when the instruction code is first interpreted by the computer, it is first sent to the instruction decoder where among all the instructions only the particular instruction that has been provided will be decoded. Then it will be passed on to the control unit, the timing and control unit, and in the timing and control unit section it issues the control signal to read an operand from the memory. Obviously we need the add operation to be carried out on particular operands. So the one operand may be available in the memory, the other operand may be available in the register of the CPU register. Usually by default register is accumulator. So a read operands from the memory will actually read the operand from the memory, the signal which signifies read operands from the memory. It will actually read the data from the memory, and a signal will be issued to ALU to perform the addition operation. This is only an overview of what is being carried out inside a general purpose computer. Now, the operation part of an instruction stored in the computer memory, it is a binary code that will be instructing the computer to perform a certain specific operation. Now here we have to understand the micro as well as macro operation, the difference between micro and macro operation. So the control unit receives the instruction from the memory, interprets the operational code bits. It then issues a sequence of control signals to initiate different micro operations. Now to perform a certain task, there may be different set of sequence of events that will take place in order to perform that particular task. So we can call that micro operations in a particular internal with the help of the internal registers of the computer. Then for every operation code, the control issues a sequence of micro operation needed for the hardware implementation of the specified operation. So for this reason, an operation code is sometimes called a macro operation. Since a particular instruction will involve sequence of events to perform that particular task, those individual tasks, those individual signals or sequence of events are summed up as micro operations. But to perform the entire task, we often call the operation code as the macro operation. Now let us try and understand a simple situation where we can try and understand the stored program organization. In stored program organization, we have considered a memory module. The memory module here you can see is having 4096 locations. Each location is carrying 16-bit data. So in this memory module, one section is the instruction where we are storing the instruction. In the in the same memory module, we are also saving the operands or the data. Now, to address this many locations, that is 4096 locations of the memory, we need 12 bits. So the address bits are 12. Now, there are 4 bits to specify the operational codes. Now we are considering 4 bits to specify all the operations that this particular hypothetical computer can perform. Now, the instruction code will then have the most 4 bits, the most significant 4 bits, that is from the 12th position to the 15th position, that 4 bits will provide us the operational code, and the next are the address bits. Now, so if there are 4 operational, there are 4 bits for operational code, then there will be 16 possible combinations of operational activities that can be performed by this particular computer. Now, these are the 12 bits which will be used for locating the address of the operand. Now, the memory of the hypothetical computer consists of 16-bit word length. So, to find out any data that has been stored in the memory, the total data width will be of 16-bit. Any operand that is stored in the computer memory is of 16-bit size. So computers that have a single processor register usually assigned to it the name accumulator and label it as AC. In our hypothetical computer, we are only having a one single accumulator. So that particular register has been shown here. The operation is performed with the memory where the data is available with the accumulator, and the resultant data is stored in accumulator itself. Now let's see how it is carried out when we go for direct addressing. Now in direct addressing, the most significant bit here is actually the bit usually reserved for showing whether the instruction is direct addressing or indirect addressing. So in this case, if we consider I to be 0, it is actually direct addressing. Now assume that there is a particular operational code, that is add, and the address given here is 457. The address given here is 457. So in this instruction code, there are 3 sections that has to be investigated, and you have to understand this properly. The first bit actually is giving us an information whether this particular instruction belongs to direct addressing or indirect addressing. If it is 0, the addressing is direct. Now the next 3 bits are providing us the instruction add. So the computer has to perform addition operation, and the next is the address of the operand. So here it has been given as 457. So where to find the operand? The operand is in the location 457. So here is the operand. Now the content across the address 457 is added with the content of the accumulator. The operand is available here. It gets added with the previously loaded data in accumulator, and after addition operation it is saved in the accumulator itself. Now let us try and understand indirect addressing. To understand the indirect addressing, the bit which signifies direct or indirect addressing here is 1. So when it is 1, it shows that the addressing type is indirect, and the operational code given here is again add, but this time the address that has been given here is not the address of the operand. It is the address of the operand. That means actual operand is across 1350. So the address of the operand actually is 1350, and in the instruction we have given 300. So across the memory location 300 we have the address of the operand. So we are indirectly pointing to the operand, where the address that has been given in the instruction is nothing but the location where the operand's address has been given. Hence we call it indirect addressing. Now the rest remains the same. After getting the address of the operand is now added to the accumulator, where preloaded data is available in the accumulator. It gets added with the accumulator and is saved in accumulator itself. So now let's move on to the computer registers that are usually available, but this is not the same for all computers. If the computer architecture varies, the size of the register as well as the number of bits that are being handled by the register differs. So it differs from computer to computer. Now let us see a hypothetical computer where there are certain registers. These are the generic registers that we are going to understand, that are usually the registers, the processor registers, are used for manipulating data, and register for holding memory address. So the memory address AR has 12 bits. Here we can see in the diagram it is having 12 bits because it is only used to hold the address, the memory address, and we all know there are 4096 locations. So to address 4096 locations we only need 12 bits. Now the program counter here is also having 12 bits. Why so? Program counter is basically used to hold the address of the instruction that has to be executed, and it automatically increments to the next instruction once the previous instruction has been fetched by the computer. Since the address width is only 12, hence the program counter in our situation in this computer is also 12 bit. The read and instruction, the content of PC taken as the address of the memory, and the memory read cycle is initiated. As we have already learned that the instruction address is actually available in the PC. So once it has been fetched from the memory using a read cycle, The PC then automatically gets increment to the next instruction in the sequence. Two registers are used for input and output. The input register receives an 8-bit character from an input device. So here the INPR, which is the input register, is usually used to hold the 8-bit data which is coming from the input devices. So there may be varieties of input devices connected to the computer. So basically it will hold the information coming from the input devices. The output register holds the 8-bit character for an output device. Now suppose there are certain output devices connected to the computer. So to send the information out of the computer, we need to have a register which will hold the information for some time so that the output devices can get the information. So the output register plays a very important role. It actually stores the characters which are basically meant for an output device. Now let us try and understand the common bus system, which actually simplifies the interaction between various registers inside a computer system. Now, most of the computer systems will have a memory module, will have internal CPU registers. Now, most of the CPU registers have different width, that is, different bits are provided to load the data, to take out data from it. So even if a register is having 12-bit and the other register is also having 12-bit, and if there are many registers in a similar fashion, then communication between the one-to-one communication between the registers will create a huge problem. Huge amount of wires will be required to provide one-to-one communication between the registers, the internal registers. So to reduce the complexity of the hardware, usually a common bus system is used. These particular bus systems, or the bus systems that are being used here, is shared by all the registers one by one whenever it is read. Now here in our hypothetical computer has 8 registers, a memory unit and a control unit. Paths must be provided to transfer information from one register to another between memory and registers. Efficient scheme for transferring information in the system with many registers is to use a common bus. Now, the outputs of 7 registers and memory are connected to the common bus. We can see here AR is one of the registers, PC is one of the registers, DR, AC, input, output, TR, IR. All these registers are actually connected directly to the internal common bus system. Now, whenever the register is required to transfer data to another register, it will initiate the data writing process onto the bus, and when the data is available in the bus, it can be loaded into another register when issuing a load signal. All the registers, memory module and others are connected with the clock as seen here. The memory unit is having a write-read signal, and it is also having bus from where it can give out data into the bus system. Also it can accept data into the memory module from the bus. So the memory module will basically have the data bus system, the address system, address bus, and read and write. The other registers which work on the clock are all connected together in a synchronous fashion, and there are other control signals like load, increment, clear, and there are certain resistors which will hold the data from the input devices and will hold the data for the output devices. There is also a unit called arithmetic logic unit, where it is a combinational circuit while arithmetic or logical operations are carried out as specified in the architecture of the computer. The specific output is selected from the bus lines at the given time is determined by the binary value of the selection variables S2, S1 and S0. Each and every register shown here are enabled by a system or the system variable which is given as S2, S1 and S0. The output of 7 registers and memory are connected to the common bus. The specific output of that is selected from the bus line at any given time is determined by the binary value of the selection variables S2, S1 and S0. The number along the output of DR, here we can see the DR data register, is given as 3. That means if the selection variable is 0, 1, 1, the 0, 1, 1, only then the data register will get selected. Here the 3 means the decimal equivalent of the binary combination at the selection variables. To select DR or to enable DR, we need to have a 3 here in the selection variables. That has been given as 3. DR is 3 means 0, 1, 1. The lines from the common bus are connected to the input of each register and the data inputs of the memory. The particular register whose LD input is enabled receives the data from the bus during the next clock pulse. Now, the memory receives the content of the bus when it writes input is activated. That means when a data is available in the bus system, it will get into the memory module only when a write signal is applied. The memory places a 16-bit output onto the bus when the read input is activated. So, the input which is available inside the memory module, the data which is available in the memory module will be written onto the bus only when the selection variable selects the memory, that is providing 111 here. When we provide 111 here, it selects the memory module, and when a particular address is provided into the address of the memory module, that particular location, the data which is available inside that particular location will be sent onto the bus after providing a read signal. 4 registers DR, AC, IR and TR have 16 bits each. Here the data register, accumulator, instruction register and temporary register all work on the operand or work on the data, hence their bit length is 16 bit. The 2 registers AR and PC have 12 bits. We have already discussed this earlier because AR and PC are basically used to hold the address of the memory module. Now, the input and output registers are all 8-bit in size and are basically used to hold the data coming from the outside world into the computer and the data provided to the outside world through the output register. The bus lines are connected to the input of the 6 registers and the memory. 5 registers have 3 control inputs, that is load, increment and clear. The input data and the output data of the memory are connected to the common bus, but the memory address is connected to AR. Therefore, AR must always be used to specify a memory address. The input from DR and AC are used for arithmetic and logic operations such as add DR to AC or AND DR to AC. So this means that a data available in the data register gets added to the accumulator, or the data available in the data register gets ANDed with the accumulator. So here we have an arithmetic operation and here we have a logical operation. Now result of the addition is transferred to accumulator and the end carry out of the addition is transferred to the flip-flop E, which is otherwise called the extended AC. A third set of 8-bit input comes from the input register, that is the INPR. So here we can see from the arithmetic logic unit we have a end carry out. So if after performing any operation, if we have a carry out from the last bit, the most significant bit, then that gets reflected in the E, which is nothing but a flip-flop, a 1-bit flip-flop. We usually call that extended AC bit, that is accumulator bit. Now let us try and understand a simple situation where we have to transfer the content of accumulator into the data register. So how that can be done? First of all, we need to provide a situation in the selection variables where it selects the accumulator. So to do that, we can see the accumulator, which is AC, is actually having a enable signal combination which is 4. That means we have to provide 100 at the selection variables. So once we do that, the enables accumulator, it enables the accumulator. So now the accumulator is ready to give out the data. Data inside the accumulator is transferred to the common bus. Since only the accumulator now has been activated, all other registers are tri-stated. Hence, only the data from the accumulator will be available on the common bus. So the data is now available in the common bus. Now the data available in the common bus system is also available at the input of the data register. What we need to do is we need to load this. So to send the data into the data register, we need to provide load signal LD. When we provide a LD signal, after providing LD signal and getting a clock, the data available in the 16-bit common bus system will be written into the data register. So this is how a common bus system works. So to summarize, we have in our lecture session we have tried to understand different instruction codes. We have tried to understand the store program organization. We have also tried to understand indirect and direct addressing using an example. We have also tried to understand how a common bus system works. So thank you very much for your patience. Hope you have liked the video, and if you have any questions, please do not forget to raise the questions in the comment box. Thank you very much.